Thank you very much, Chair, and thank you for the organisation of today. Greetings, everybody, and welcome. I'm Tim Dixon. I'm the head of IEAGHG, and my role today is to provide a overview and update on global CCS developments worldwide. Keyboard. Okay. First of all, just to say that my organisation, IEAGHG, we're an international research organisation in CCS. We've been around since 1991. We were set up by the International Energy Agency, but we are not part of the International Energy Agency, so anything I say does not count as their views. But we do use their material, and they use our material. And our role is funding research in carbon capture and storage. And just for those of you who may be new to this topic, I'm going to give a very brief introduction to what carbon capture and storage is, why we're looking at it as a planet, and then some of the regulatory developments briefly. Jill Hyun's covered those well for the London Protocol, and then I'll give an update on the global developments in projects. So carbon capture and storage essentially is capturing carbon dioxide, the main greenhouse gas, capturing it from large point sources and injecting it deep beneath the ground so that it does not act as a greenhouse gas. And so any large point source of carbon dioxide this can be applied to, for example, power generation from gas, coal, or from biomass, from industrial processes such as gas processing, from industrial processes such as cement production, where there is no low-carbon alternative, iron and steel production, and it can even capture CO2 from the atmosphere through direct air capture. Now, that's the cartoon that describes CCS. The one thing wrong with that cartoon is the scale of the storage, because we inject at least 1,000 meters deep. And this is to scale. This is a real project based in Canada, onshore project, capturing CO2 from a coal power station that's injecting 3,000 meters deep. And it gives you an idea of the geology. There's many different geological formations between the reservoir and the surface, some of which are potential reservoirs, some of which are trapping formations. And understanding those is really important in the site characterization aspects of permitting CO2 geological storage. So why are we looking at it? Well, we go to the science of climate change and the Intergovernmental Panel on Climate Change, IPCC, and in all of their scenarios, there is a role for CCS being applied along with all the other CO2 mitigation and greenhouse gas mitigation technologies. And what they do point out as well in different reports is that if CCS is not in that portfolio of mitigation technologies, the costs of achieving the climate goals increase significantly. This was carried through into the most recent IPCC reports in the AR6 series, again highlighting the role for CCS along with other mitigation technologies, but also pointing out that on the planet, the geological storage capacity is around 1,000 gigatons, which is far more than is actually needed for its role in these scenarios if we were to achieve the more ambitious goal of 1.5 degrees C. But in their good work that draws upon just peer-reviewed literature, they also point out that there's not enough policy instruments in place to stimulate CCS projects. My colleagues in the International Energy Agency, they produced their own scenarios and reports, and in 2020 they produced a special report on CCUS, and I think they summarised nicely why people are looking at this and trying to deploy it as a technology, because it can be retrofitted to existing CO2 sources, so you can tackle emissions from your existing energy assets. It can be bolted onto the chimney, basically. Also, really importantly, whilst in the power sector, we have options for low-carbon electricity generation from wind and solar, hydro and nuclear. With some industry sectors, there was very hard or no options to decarbonise. As I mentioned, cement and steel. And there's a possibility of decarbonising aviation through the creation of synthetic aviation fuels as well. Hydrogen as an energy vector has a potential lot of applications, again in the hard-to-abate regions and areas such as heavy transport, ship transport, domestic and industrial heating, and CCS on natural gas can also provide low-cost, low-carbon hydrogen, and removing CO2 from the atmosphere through direct air capture or bioenergy with CCS. So that's why people are looking at it, along with the other mitigation options. Ready for the COP in COP26 in Glasgow, the IEA produced their net zero roadmap for the energy sector, because the energy sector is the main source of CO2. And in that got the headlines, because you may remember it said about no new developments of new oil and gas fields within this. Should be needed if you do all of the things they put in this roadmap. But within that, by 2035, for CCS and carbon dioxide removal, 4 gigatons per year would be captured. Now, the 4 gigatons a year is 100 times more than we're doing at the moment from the projects we have. Just bringing this up to date, the International Energy Agency realised that we're not on track in general in terms of mitigation, and so they produced their credible pathways to 1.5 for actions to be done this decade by 2030, and there are 4 pillars for action: decarbonising electricity, reducing deforestation to zero, tackling methane emissions, and carbon management through carbon capture and storage and carbon dioxide removal. And this got encapsulated by an initiative that the US launched at the Major Economies Forum in April last year, the Carbon Management Challenge, and this was then launched at COP28 in Dubai, the UNFCCC COP. And of note here is not so much the 19 countries that have signed up to scale up CCS and CDR, but the fact that in the lead countries, US, UK, Canada, also Brazil and Indonesia leading that, 2 developing countries. So that's the need. My colleagues also updated their roadmap. The scale of CCS, the role of CCS's participation has gone down because projects have not been built since they developed the last roadmap 3 years ago. And whilst the project pipeline is increasing in terms of projects being assessed, feasibility studies, development, if all of those projects that are in feasibility stages now were to reach investment decisions and construction and operation, that would still only be 1/3 of what's needed in their net zero by 2050 roadmap. So we're not doing enough. And the IEA World Energy Outlook also summarises on CCS that current policies are wholly insufficient. So that's a scene setting on why we're looking at CCS. The UNFCCC Paris Agreement that we're operating now globally for the climate targets based upon the nationally determined contributions. In those those NDCs, which are looking to 2030, only 23 have explicitly got CCS in. And you might think that's low, but these are NDCs that are looking at mitigation actions just in this decade up to 2030. The Paris Agreement also requires countries to put in place their long-term strategies to mid-century, and here a lot more of these have CCS in. 71 countries submitted, 48 have CCS, and that's because countries are realising that they're doing the easier to do mitigation now. They've got to go beyond that to achieve the net zero by mid-century. They've got to apply CCS to the hard-to-abate parts of their economic activity. So really importantly, from the London Convention, London Protocol's perspective, how do we ensure environmental protection? How do we ensure that geological storage is safe and secure? And we now have a range of international regulations. I have to say that the London Protocol was the first in 2006. and Ju Hyun's given a nice description of those. The UNFCCC included it in the Kyoto Protocol from 2011 for developing countries. And we now even have ISO developing standards for capture performance, geological storage, pipeline transport, etc. And several countries have also got, and regions have got, regulations on geological storage. The EU with the CCS directive, the US with its EPA storage regulations, Australia, Japan, Canada have as well. And all of these are based upon the IPCC's Greenhouse Gas Inventory Guidelines that updated its chapter with a new chapter in 2006 on CO2 geological storage. And I should mention here, for countries that do not have regulations in place yet, my colleagues in the International Energy Agency have a handbook on how to develop legal and regulatory frameworks for CCS that was updated in 2022. So just go back a step to why we're looking at CCS, and the IPCC did a special report in 2005, and they did conclude that it was worth pursuing as a mitigation option, but for well-selected, well-designed and well-managed sites. That's the role of regulation, to ensure that project operators select sites well, design them and operate them well. I made reference to the IPCC guidelines for greenhouse gas inventories. They looked at they produced the guidelines that every country follows to report every greenhouse gas emitted in a country's jurisdiction. For CO2 geological storage, they realised that an emissions factor-based approach would not work. It has to be on the more rigorous Tier 3 approach, which is based upon measurement and monitoring. And this is the methodology they came up with around site characterisation of the geological storage site, assessment of the risk of leakage, simulation and modelling of the CO2 behaviour in the storage reservoir, a monitoring plan, and then reporting of both the CO2 injected and the CO2 should it leak from the storage site or from the injection processes. And for appropriately selected and managed sites, this supports a zero leakage assumption, unless the monitoring indicates otherwise. And this basic methodology underpins all of the regulations that were developed since, including those of the London Protocol. Ju Hyun's covered the London Protocol developments very well, so you know the history there, and the amendment in 2006 to the annex to add CCS, the CO2 specific guidelines produced in 2007, and it moved relatively quickly. And I like using this slide. It's 2005 slide from Plymouth Marine Laboratory, but it's in the consideration then by the scientific group here. We were looking at the risks to the marine environment of storing CO2 in the subsea bed. What happens if CO2 leaks into the marine environment? That coincided with the realization about the impacts of the CO2 from the atmosphere being absorbed by the Earth's oceans and the causing ocean acidification, particularly in the surface layers of the oceans. And this slide shows the range of surface layer pH over 20 million years. And then in 2005, we were about 370 parts per million, 380 parts per million CO2 in the atmosphere, and we'd already moved the surface layer pH out of its 20 million year range. Obviously now, we're in 2024, we're at 420 parts per million, moving it further out. That has significant implications on seawater chemistry and on the ecosystems and on things that form calcium carbonate bodies such as phytoplankton, and there's a photo of a coccolithophore there, that if we get much further, the seawater chemistry will work against their formation of their bodies, their shells. So that realization about the damage we're doing through atmospheric CO2, I think, was a stimulus to the London Protocol moving on this one particular technology that was in this context as well. And also why we want to ensure there is no leakage of CO2 from the subsea bed. Just to show you the detail of the amendment, the term overwhelmingly was put in there to define the CO2 stream. but acknowledging that there may be incidental associated substances from the source material and other factors involved in the process. And really importantly, no other waste can be added for the purpose of dumping. The level of incidental associated substances should be based upon their impacts, both on the marine environment and human health, but also their impacts, potential impacts on the integrity of storage sites and the transport infrastructure. And that's a reference there to the scientific group meeting that developed those. OSPAR is the regional translation of the London Protocol for the North East Atlantic. That moved very quickly afterwards, following the similar requirements for permit issuance, and actually going a bit further to explicitly prohibit storage in the water column. And both London and OSPAR have their guidelines for issuing permits. They're basically an environmental impact assessment process. Joo-Hyun mentioned these and showed this slide as well, showing the CO2 specific guidelines requirements conclude with an impact hypothesis that should be produced before a site is permitted. So, coming to what IEAGHG, my organisation, does in this arena, is we fund research and provide evidence base around carbon capture and storage and carbon dioxide removal where it involves geological storage of the CO2. And being a participant in these meetings, we heard regularly the requests from Greenpeace in particular for sharing of experiences, for sharing of the permitting information from the offshore projects that were being developed or were operational. So our contribution was to look at one project site that had been permitted, and that was in the Netherlands for the road CCS project using the P18-4 field offshore. They'd got their permit from the Dutch regulator. The European Commission had given them approval or an opinion positively as well. Now the European, so I mentioned the London Protocol requirements. The OSPAR requirements are very, very similar. And because most of the OSPAR parties are European member states, the European CCS directive also reflects the OSPAR requirements, which reflect the London Protocol requirements. So our logic was, if they've got approval under the European CCS directive, they should be meeting many of the requirements of the London Protocol. But how do we know? So we commissioned TNO, a Dutch agency, to look at the permit documents for the road project site. There's 1,100 pages in Dutch, and they went through and they assessed those against the 56 requirements of the London Protocol CO2 specific guidelines to see whether these 56 requirements were met. This was a qualitative assessment more than a quantitative, but the specific guidelines requirements themselves are also qualitative in nature and not quantitative. And in their conclusions, then, looking at this, they did conclude that of the 56 requirements, about 80% were met. There was sufficient information to make a reasonable decision that there was a positive conclusion, and that the Dutch regulator was involved in this process, this study as well as the Dutch operator of the project. But there was about 18% of the London Protocol CO2 specific guidelines requirements were only partially met or incomplete. So we've separated them into the consideration of the waste, physical and chemical properties, the action list, characterization of the subsurface, assessment of potential effects, monitoring and mitigation, and the permit conditions. And there was a small number that were not met of the CO2 guidelines requirements in this. So what obviously is most interest is the partial or the non-met requirements of the 56. And the report highlights these. It includes the looking at other disposal options. But if I remind you that the London Protocol concluded that the decision on which CO2 streams should go for offshore storage is really up for a country's energy and climate policy, not for the London Protocol. So that's why that was not included here. The second one, on the toxicity and potential for bioaccumulation, the storage site that the P18 field is I think it's about 20 kilometres offshore, but it's 3,000 metres deep. It's a depleted gas reservoir, under pressured because of the natural gas has been produced, with a single well for access. And they concluded in the site characterisation and the risk assessment that there was negligible risk of leakage. And so their environmental impact assessment aspects were only partially covered because they just could not see a scenario for the CO2 getting into the marine environment from the storage reservoir. And that's part of the explanation for why that information was not provided to the Dutch regulator within the environmental impact assessment that was provided and undertaken for this specific project. The one thing that was not included was the requirement for permits to be reviewed at regular intervals. So that's on the regulator to require that, and also the national action list aspect, the development of a screening tool. Again, that was on the national regulator to have that in place for the Netherlands. They didn't make reference to it in the documents for this particular project. So anyway, I recommend this report. We had it presented by TNO in the annual meeting of the contracting parties to the London Protocol, LC 38, I think it was, in 2016. And it's freely available, and I wished it would be included in the considerations for the ongoing correspondence group work on permitting experiences. And also because this work is, whilst the road project did not proceed, the same storage site is the one that's being used for the Portos project in the Netherlands that is proceeding. So whilst it would have to be re-permitted because the CO2 streams will be different going to that, the basic facts around the storage site would stay the same. So its relevance is still there for the Dutch regulators to draw upon, or for the wider world to draw upon. It did produce some recommendations in the report, like it should be more explicit about meeting the London Protocol requirements. It should highlight the impact hypothesis at the end, although they did say also in the report that the conclusions of the risk assessment process in effect are the impact hypothesis, but it needs to be more explicit. Because they considered that there was negligible risk of leakage, they didn't do a site-specific impact assessment on the marine environment, but whether the data that we've got from other projects, sites, such as STEM CCS, could be used in its place, and the question of the action list and updating permits on there. Also in the London Protocol CO2-specific guidance is a requirement for an economic feasibility aspect, and they queried what really was that background to that, and the role for public participation could be clearer, although that's a really important aspect of offshore projects. Joo-hyun mentioned the export amendment as well. Thanks for that update, and that's the details of that. And just wanted to thank my colleagues here at IMO and for co-authoring a report, because we realised also that for the wider world, the guidance documents that were amended for export and for transboundary CO2 storage, they're buried in the annexes of London Protocol meeting reports. So we've drawn them out into an IEAGHG report that's available with the full references back to the London Protocol documents themselves. In terms of export of CO2, Joo-hyun mentioned the first bilateral agreement between Denmark and Belgium. Also this year, there has been a bilateral agreement between Denmark and France. And on Monday this week, there was a bilateral agreement announced between Netherlands and Norway. And also in this context, sorry, I don't have a slide on this, but the European Commission did its own analysis in 2022 and concluded that the CCS directive worked as an appropriate arrangement, because there needs to be an arrangement or agreement in place to make sure that all the permit conditions are met. The CCS directive in Europe serves as an appropriate CCS arrangement, and it's just that other aspects not covered by that should be covered by these bilateral agreements. And that's essentially around the permitting responsibilities between the two parties. And to my reading of those three MOUs, each one of those does specify the permitting responsibilities. So the last thing I'll say in 5 minutes is just a quick global update then. My colleagues in the Global CCS Institute produce a great report every year on the global status of CCS. Yes, there's only 41 projects in operation, but there's over 300 in different stages of development, many in Europe and North America. But what we do as IEAGHG, we do have a specific workshop series looking at offshore CCS, offshore geological storage in particular. And this was set up with the University of Texas and stimulated by a recommendation from the Carbon Sequestration Leadership Forum. And we held our 6th workshop in this series in September last year, hosted by the University of Aberdeen here in the UK. So this was set up as a request from the Carbon Sequestration Leadership Forum around international knowledge sharing. Why are people looking offshore for geological storage? Well, this is a geological map of sedimentary thickness showing the potential storage globally. But what's significant, there are several benefits, including that the ownership of the pore space is more straightforward offshore in many countries compared to onshore. Also, the proximity of the storage geology to major industrial sources of CO2 that are often along coastlines as well. So in this workshop series, I won't go through these in detail, but the first one we had in Texas in 2016, 13 countries attended, and these workshops were about sharing knowledge between those countries doing the offshore projects operationally and those countries who are interested. So we had 4 projects operational offshore in Norway, Japan, and the Netherlands, and so it was about sharing their experience and knowledges with other countries. The second workshop the following year was also in Texas, and IEAGHG, we produced reports of these workshops. We try and draw conclusions and recommendations at the end, and they're public reports on our website. The third workshop was hosted by Norway. The fourth workshop was also hosted by Norway in 2020 and was in conjunction with the EU's STEM CCS project, which was a large controlled release of CO2 in the North Sea seabed to test monitoring sensors and techniques and mounts and methods for detecting leakage of CO2, and it produced a lot of really good work, and we do have confidence now in offshore leakage monitoring and quantification through the results of the STEM CCS project. For that meeting, we did a quick map. This was thanks to an intern at the University of Texas who just put on the map countries who are active in offshore storage, sorry, Brazil as well, and also the countries in blue are the ones interested. And the US very much wanting to learn from other countries in this scenario. Our next workshop was back in the US in New Orleans, just after COVID. That's the range of topics we looked at, similar for each of these, including an international project roundup, where we get updates from projects. And the last workshop, as I mentioned, was in Aberdeen last September, where we had the project roundup. We looked at monitoring developments, we looked at transport developments, interaction with other users of the seabed, in the UK, North Sea perspective in particular, with offshore wind, legal and regulatory and accounting developments, environmental aspects as well. And that report is available from us. I think we had 60 people in person and 130 people online for that hybrid meeting. The projects we looked at, we had updates from in that meeting, were from the UK, Greece, USA, Portugal, Norway, South Korea, Netherlands, Australia, Taiwan, Australia and Timor-Leste in Southeast Asia. We had updates from all of those from those organisations on the right-hand side. And we also provided summary updates from other projects who were not able to give updates, including the two long-running projects in Norway, Sleipner and Snøhvit, but also the ones being developed in Denmark of notable importance there. So with those projects, that's a lot of activity. There's only 4 of those are currently operational, and the others are in different stages of development and feasibility study or construction. We had a colleague, Naomi Clark, an intern at IEAGHG, very kindly produced this map of the projects under development that was shared at this meeting. The colour-coded dots, if you can see those, are yellow for use for storage in deep saline formations. Red is for use of depleted oil and gas reservoirs, and purple where there may be both, or grey where it's uncertain. But that's the distribution of projects operational or in development around the world at the moment. And Naomi also looked at the characteristics of those about 30 projects. About a third are using deep saline formations, 53% using depleted oil and gas fields. In terms of transport of the CO2 to the storage site, about half are through pipeline, and about a third are through ship and pipeline, and about 10% planning on ship-only use. In terms of the infrastructure, 55% were going to reuse existing infrastructure, and about 16% said it was going to be new infrastructure. So some characteristics there of the storage project side. And in the conclusions from that particular meeting, interesting number of projects in development, but we come back to that's still not enough projects in order to meet the scenarios that the IEA and IPCC have for CCS rolling climate targets. Spatial resource allocation is a strategic issue around uses of the seabed and the subsurface there. So collaboration between the different users is really important. It does take time to apply for licenses and permits, and in the UK case for the North Sea Transition Authority, in their permitting operations, they've worked out a way through issuing a few permits on an ad hoc basis to improve the process, to take a year off that permitting process. The fact that the just transition for environmental justice in terms of human population and workforce is being recognised within CCS projects, especially in the US, where it's a requirement of the US Department of Energy. The monitoring plans are maturing and being approved by regulators, and that sets a precedent for the level of detail and requirements that are needed. And I personally noted that some of the MMV plants now are making use of the tools developed by the STEM CCS project. Community benefits are key still, even with offshore storage. The fact that we've got the tools for environmental monitoring, but the gap is some development of some monitoring techniques for use around wind farms, where a geological storage formation may have a wind farm on the seabed above that. It makes using seismic techniques more difficult. And just to end with, the next workshop in this series will be in Texas again at Port Arthur in September this year. You're all very welcome to attend. And more than that, we welcome suggestions for agenda items that we can address in this meeting. And so the points made by Greenpeace on Monday, I would like those again. I made a good note of those, and we'll look at those areas and see whether we can make agenda items to discuss those in more detail based upon the experiences that we've got or the gaps that there may be and how we can address those. So that's a quick review of global CCS developments offshore, and happy to take any questions. Thank you very much, Chair.
Thank you, Mr. Dixon, for the overview of global CCS developments, which serves to set the scene for the day. I would now like to open the floor for any questions on Mr. Dixon's presentation. Greenpeace, you have the floor.
Thank you, Chair, and thank you, Tim, for such a comprehensive opening presentation. We're particularly pleased that you raised again the TNO study. We were very grateful at the time that that was something that had been organised because we felt that there was almost an assumption that everything would go right and therefore certain things in the assessment weren't perhaps so necessary. But we always feel we should be asking not just what do we think, but how do we know and what happens if we're wrong. And I think that those kinds of questions do get at those issues. And I think I would agree with you that it would be great to have that report as part of the CCS discussions going forwards, because I think it did have some very important guidance and lessons going forwards. I had 3 questions quickly. Firstly, you mentioned the 4 pillars, among which were decarbonising the energy sector and carbon capture and storage as part of that. If we don't find a way to limit the application of CCS to hard-to-abate sectors rather than retrofitting to fossil fuel power, how do we ensure that we're not working against decarbonisation as a priority? Because I think if it remains a possibility that any source of CO2 is possible, we may not be able to break the link with fossil fuels. Secondly, as things stand, and I'm glad you also raised the Global CCS Institute reports. They're a very valuable source of information on global developments. But at the moment, what those show is that still the majority of CCS is used for enhanced oil recovery. Now, that balance may change in the future, but is there a way in which that there can be a clearer break between enhanced oil recovery and the kinds of approaches that you were focusing on today? Or is it always going to be the case that enhanced oil recovery and therefore more exploitation of fossil fuels is going to be linked to CCS? And the final thing is, although we understand, of course, that CCS relies on the assumption of zero leakage, what can we do if it does leak, other than controlling the well pressure or perhaps stopping injection? Are there other opportunities that are emerging or being investigated as to what could practically be done if there was a leak that was not associated with the well itself, but something further away from the injection site? What are our options at that stage in order to stop the leak getting worse? Thank you.
Thank you, Greenpeace. Mr. Dixon, would you like to respond?
Yes. Thank you, Chair. Thank you, Greenpeace, for those questions. On the hard-to-abate topic, I think there's two aspects to that. We want to decrease the use of fossil fuels in general, but even with the most optimistic renewable electricity provision, with variable sources of wind and solar, there needs to be some balancing of supply of electricity. And so many economies are looking to gas with CCS. Or if you're going to use gas power generation, you need to decarbonise that to achieve net zero. And so that's the potential for it being used there. And really it's up to countries to decide on how they decarbonise. And what's important is the CO2 emissions to the atmosphere, because that's what's causing global warming and climate change. With the EOR projects, historically, the operational projects were EOR-based, but most of the new projects around the world are not EOR-based, they're straight storage-based, and the incentives for new projects are very much steered to straight storage. And if you look at the US incentives, for example, their 45Q tax credits, just don't quote me on the numbers, but I think it's about double for straight storage compared to storage through enhanced oil recovery. And all of the new projects under development in the US, my understanding is they're all straight storage for that reason. And all of the offshore projects, the 30 projects we just described, they are all straight storage as well. So the future is not EOR, as far as I can see, it's straight storage. And on your last question, this is a really important question that we've been looking at with others for over 20 years about if there is leakage. So firstly, the most likely leakage path, should it occur, will be through the engineered barrier in the cap rock, the well. We do have good experience in well fault remediation for the oil and gas industry experiences. We have confidence in that being able to be undertaken for CO2 leakage through wells, but it is the major focus in the risk assessment on every CO2 geological storage project. Absolutely. For non-well leakage, that is much harder, as you imply, to deal with. But when we're looking at CO2 in the subsurface, what we've realised is that it is a reactive compound. If the likelihood of it reaching the surface through other routes is very minimal, there's many things that will happen to it on the way between a storage reservoir 3,000 meters deep in the surface, such that it's very hard to create a scenario where it does reach the surface. Nonetheless, we need to be ready for that, and the monitoring techniques and tools have been developed, including for large area surveys, should they be needed, using AUVs. And the scale of such leakage would be minimal because of all the processes that would happen to the CO2 between the reservoir and the surface as well. So that was partly in the conclusions of the IPCC inventory guidelines work in 2006. But it is, there's the right questions to ask, and there's a lot of research dollars have gone into that area, including, as I mentioned on Monday, we've had to engineer and create leaks in order to test these theories onshore and offshore, so that we can have confidence in the monitoring in particular. Thanks.
Thank you, Mr. Dixon. Kenya, you have the floor.
Thank you very much, and thank you for the good presentation. My question would be on the use of CCS on ships, and kindly if you could advise, how do you see CCS being used on ship as one way of addressing climate change and meeting our decarbonization targets? And also, what would be the requirements for the ships transporting the captured carbon to the site? Thank you.
Okay. Thank you for that interesting question. CCS on ships is actually a topic that's been looked at because of the emissions, the CO2 emissions from ships, and techniques are being developed. And there is the potential for CO2 capture of the CO2, and then when the ship gets to port, it can then unload the CO2 at an appropriate facility for geological storage. And in fact, one of the projects being developed at the moment is the Northern Lights project in Norway, which is designed specifically to receive CO2 by ship from other sites in Northern Europe. It's very good because it's enabling CO2 capture to be fitted at industrial sites that might not have wanted to develop their own site-specific storage. And then the 2 ships that are being constructed for that transport of CO2 at the moment, but those ships have just been launched in the last 2 weeks, still being fitted at the moment. But the next series of ships they're looking at would have CO2 capture built onto them. And I don't know the technique yet, but that is a serious consideration by that project. And in terms of requirements of the ships for transport, we do have a presentation later this morning from Sean Bond from ABS Europe about ship transport. So he's better placed to answer those questions. Thank you.
Thank you. Germany, you have the floor.
Yeah, good morning to all, and many thanks to Tim for your very informative presentation. I would like to keep on discussing this issue of hard to abate emissions. And my question is actually, so you did not really give an answer to the question by Greenpeace. You said that we need to see that it's hard to transpose the production supply of electricity from now fossil fuel to really renewables in a very quick period of time. So this is difficult. So we need CCS for the sequestration of emissions from electricity production, and then it's also an issue for the national policies. But I would like to ask, is this not one of the most important questions with regard to carbon capture and storage, for what emissions we would like to use this technology? We have 3 options for all emissions. We have the option to use this technique to sequester hard to abate emissions, and we have also the option to use it to achieve negative emissions. So we have 3 options, and how to deal with these options in order to come up with a clever and reasonable climate change policy. Is this not an issue which needs to be scientifically investigated? And so this is the answer to this question is yes or no, but maybe you can elaborate a bit more on that. So this is my first question. And secondly, you did not really mention so much the option of CCU. So in you talked about one strategy and with four components, but in this strategy CCU was not mentioned. But how do you see the relationship between CCS and CCU in the next years? Many thanks.
Okay, thanks for those questions. Again, I would start with, it's up to each country on how it decarbonises its economic activity, industrial and power generation. My point on the renewable energy supply of electricity, of getting the maximum electricity from renewables is obviously ideal. I think when we were here on Monday, I don't know if you know, but the UK had 72% of its electricity from renewables on Monday. It was very windy and it was very sunny. But we have to have something supplying electricity for when it's not sunny and when it's less windy. And that's the role of power generation from fossil fuels then. There's still likely to be a role, and that needs to be decarbonised. And you can't say that it's, hard to abate sectors, you need to decarbonise those, but it's no better to say don't fit CCS to fossil fuel power generation. That CO2 is just as harmful to the atmosphere. And as I think we had in some of the discussion on Monday, the negative emissions aspect, the IPCC and the IEA do say that that there are some greenhouse gas emissions that we do not have ways of mitigating, particularly from agriculture, for example. To achieve net zero, we do have to be able to go negative with some technologies. And so CCS it forms a way of doing that through direct air capture or biomass with CCS BECCS. But it really is up to each country's climate policy on how they achieve net zero within the emissions that they can control within their jurisdiction. On CCU, carbon capture and utilisation, that's not all CCU results in mitigation of CO2 emissions. As an organisation, our remit is around the mitigation of CO2 emissions. And the role of CCU also in whether CO2 is locked up in products or in processes, the question is the permanence of that CO2 removal, because the CO2 removal needs to be from the atmosphere, kept from the atmosphere for 4,000 years plus, but its storage in products doesn't necessarily guarantee that at all. And the permanence issue is core to that. So that is why the CCU is less addressed maybe in all the analysis that I've mentioned, is that it doesn't result in large-scale mitigation of CO2. And that's what we're here to do.
Thank you, Mr. Dixon.